is it shifts your linear model. Um, so like, let's see here. If we just have y equals mx plus b, let's say we've got y equals x, like in the simple case. So 1, 2, 3, 1, 2, 3. In this case, your theta is 1, y equals x. So that gets you this line. This is y equals x. If you were to do y equals x plus 1, then this same line exists, it's just shifted up. Your y-intercept is higher. And so the same kind of thing happens with higher order polynomials. That bias term is going to enable you to shift your model up or down, depending on if it's positive or negative. So the y-intercept will be the same for each feature. Don't think of the y-intercept as being something for each feature. It is just another theta value that you learn. So if this is your input matrix, your theta matrix would be theta 0, theta 1, all the way down to theta n. This is your bias value, and you learn it. So for a problem, so like each, you don't really have to think about it. You just, as long as you set the problem up correctly, it will fall out of gradient descent. But if you want to think about it, each problem, each synthetic, or the Wine dataset, the synthetic dataset, every dataset is going to have a bias term associated with it. But it's something that you'll learn. Hopefully that clears things up a little bit. Cool. Now the thing is, well, we're going to have more bias terms. Generally, in every machine learning model that you make, you're going to have a bias term of some kind. And for the most part, it's always going to be treated like this. It's just another parameter that you end up learning, but it assumes that you have like an input value associated with it that's like 1 or -1. Something where the real value is encoded in this weight. But it does act differently. It does different things based on your type of model. So when we talk about neural nets today, there's a bias term in your neural nets, but it does something very different. But anyway, I'm getting ahead of myself. Any other questions about the assignment, about linear regression? Let's see, questions about process some information. If that's a question about like how do you process the data, or what are the various ways that you could pre-process the data? So I will say that yeah, so actually I can't remember. For the synthetic data, I know you can get away without doing any pre-processing. Like, you can also easily do the assignment with pre-processing. Let me see here. I'm curious if I pre-processed the wine data. Yes, I did. So the wine data, you likely do need to pre-process because it is, like, there are different scales. The values are relatively small, but it's still, like, most stuff is between 0 and 1, some stuff is between 0 and 14, and these things can all be, normalized. What I did was a very, very simple normalization. I just divided everything by the max value for each feature. So each feature became a percentage of the max value. Not great, but it does the job. I was able to hit the benchmarks without pre-processing. Yeah, and like the benchmarks, as always, I think my benchmarks are very generous, and so I wouldn't be surprised if you could. Any limits to how long we should train? Ooh, sorry, hold on. We're just going to boop. Ah, that felt good. That felt good. Okay. Where was I? Yes, any limits to how long you should train? Honestly, as long as you want. But like how I usually approach this is I set a very long time and I kind of watch it converge. Because for these problems you can do that. You can watch it converge, and it'll get to a point where you see it's not getting better, and at that point you can stop and just output your weights and be done. For context, my long time training was 200,000 time steps, where a time step is a single example. So that's going to translate into like 20,000 epochs for the synthetic data, and for the wine data, I forget how much wine data there is. But yeah, so 200,000 time steps was good enough for me on all cases. When is the next quiz? Hopefully after the one-day spring break. Yeah, that's what I'm leaning towards, is after the one-day spring break. Because honestly, this next little bit, there are going to be a lot of... there are going to be a lot of assignment, like stuff that we do for assignments. So I'll probably hold off on the next quiz for a little bit. But yeah, it is coming. There are 1,599 examples in the wine data set, so yeah, at 200,000, that's going to be like... Is that 2,000 epochs? No, that... Why is math so hard? 2,000? Yeah, okay, so that's about 100 epochs. 100-ish. 100 epochs for the wine data set, but even then, like, that's able to do the job. Yeah, these are not meant to be super difficult data sets to work with, but what they do is they can do a really good job of illustrating just the flexibility of linear regression and gradient descent. Any other questions? Any others? Oh wait, let me see if I can remember some. Oh yes, okay. So some of the common questions I've been getting from emails. So there is one question about like where do you get the theta values for the higher order polynomials? So that's something that I still think I mentioned it in the write-up of the assignment, but for your higher order polynomials, your x squared, x cubed, x to the fifth, remember, you're just creating those features. You're saying, oh, okay, I know what x is, so I'm going to create a new feature that is x squared, or x to the third, or x to the fifth. But when you do that, you also need to create all of the smaller polynomials as well. So in the x to the fifth case, you would also need to create a feature that's x to the fourth, and another one that's x to the third, and then x squared. Because that's your full model. Your new equation that regression model that you're learning is essentially y equals theta 0 times 1 times x 0 plus theta 1 times x plus theta 2 times x squared plus theta 3 times x cubed plus theta 4 times x to the fourth plus theta 5 times x to the fifth. And so naturally the follow-up to that question is, or to that answer is that, yeah, you also have a theta value for every one of those features. Every time you add a feature, you add a theta. So those dimensions should match. And let me think here. Were there any other common questions? There was another common question about how to test, which I will briefly mention. So testing this data is very, very easy because you just, like, once you have your weights, once you have your learned weight matrix, or however you want to do it, but if you're using a matrix, then testing a single data point is just a matter of calculating the, first calculating the dot product, the output of your model, so the dot product between your input and your thetas. Boop. And then you calculate the squared error. So difference between your prediction and the true value for that data point. I ask you to report the mean squared error, so you would need to do that for your entire data set, and then report the average squared error over everything. So not too difficult. The key there, though, is make sure that you're not dividing by 2 times the size of the data set. Just divide by the size of the data set. That 2 only exists in the cost function, and it only exists to make the derivatives easier. Something else that we're going to see for neural networks as well. Okay. Yep. So if you have any more questions about that, please let me know. I am glad that so many people are working on it early. That makes me happy. But yeah, I want to make sure that you have... or that the assignment is as clear and as possible, and everyone kind of knows what they're supposed to be doing. Okay. Well, now, let's get back into neural networks. So last time, I got to have my little mini rant about the naming of neural networks. We've talked a little bit about the history of neural networks. They occupy a rather dubious place in AI history, in that they were one of the causes of the AI winter, their limitations, but they have since come back into prominence, and now they are by far the most popular machine learning method out there. And despite the fact that there is no free lunch, and there is no machine learning model that is inherently better than any other, practically speaking, you'll find that, in general, neural nets are going to be the first place that people run to. So it is, of course, very important to understand how they work. Now, there are, generally speaking, 2 types of neural network, and in this class, we will go over both of them. Although we'll go over one in a lot more detail. So the first type, and this has to do with the day's question. So the first type is a feed-forward neural network. And the second type is a recurrent neural network. Can anyone venture a guess as to what the difference between these might be? Just based on the name. Neural network and recurrent neural network. And maybe if it makes things easier, I will go so far as to say that recurrent neural networks, those are my favorite types of neural networks. Although with transformers now, the calls into question whether you need any recurrence at all in order to do the things that I want to do. The direction the network is trained, not quite. What you'll find, and it's actually pretty interesting, that both types of networks are trained in a similar fashion. They go both for you, so like you run the network forwards and then you train by going backwards. So no, the main thing that's going on, the main issue is, or the main difference between them is just how information flows through the network. And so in a feed-forward network, this is typically represented as a directed acyclic graph. So it is a directed acyclic graph. Inputs flow one direction to some set of outputs. So you have your input, it goes through the network one way, and then you get some output, and you're done. It looks something like this. So I should also say that, oh no, there's not another weight there. There we go. I've messed this up, whatever. So fully connected graph structure. But the important bit is that your inputs go to your outputs, and that's it. Feed-forward neural networks are excellent for both regression and classification, and that's kind of it. That's what they do. So this is good for regression and classification. And this is what we'll talk about first, feed-forward neural networks. Recurrent neural networks have a they have a very different structure, and it's based on how the inputs work. So in a recurrent neural network, you have your input, it flows into the network, which we're just going to represent as a box. It produces an output, but then, boom, that output is used as your input the next time you use this network. And so the name recurrent is there because, because of this reusing. So you go from input to output, output goes back to input, which generates a new output, and on and on and on and on and on and on and on. So the output at one time step is input at the next. Any idea what kind of task this network would be suited for? Given how it works, what do you think what do you think we use this for? And I will say that these are used quite frequently. Although again, transformers, man. So what is a use case where I would want to give a network some bit of input? Unsupervised learning, text generation. Yes, both of those are great. So yeah, you see this all the time in sequential generative problems. So RNNs by themselves aren't super great at regression or classification. Actually, no, I take it back. You can modify them for regression and classification pretty easily, actually. But they do have this requirement that they are almost always used for sequential data. So data where its placement matters in a sequence. They're also used, as was said, like in text generation, so for generative tasks. And this is the reason that I find them especially interesting. You can use RNNs to do all kinds of cool stuff. So you can use it to generate text, which is what... so there is an assignment on RNNs, and you'll be doing text generation. Be generating some Shakespeare. Classic task. I've seen people use RNNs to generate music. Interesting music, but music nonetheless. I've seen RNNs... Oh, what else was it able to... So technically, I've seen RNNs that are able to create images. So image creation, yeah, that's a more interesting thing. So I saw this one network that was trained. You could give it a textual description of an image, and it would then create that image for you. It was really cool. But all of that data and all of those tasks are sequential in some way. The order that the output is produced matters. And so we have to treat them slightly differently than we would a feed-forward neural network. So those are the two classes. Now inside of these you have like not infinite, but all kinds of variations on a theme. But at their core, they're still going to act, like this. All feed-forward neural nets, the input is going to flow one way through the network to produce some set of outputs. An RNN, the information is going to flow forward and then go back to the beginning and just repeat over and over and over again. What kind of neural nets are used to play Mario levels? So those are, they are feed-forward... actually, no, you could use either. So the real answer is... what they're actually doing is reinforcement learning most of the time. And depending on the type of reinforcement learning that you're doing, because there are multiple types that you can do. You could either use a feed-forward neural net, and excuse me while I throw out a bunch of jargon for you. If you're doing, like, Q-learning, then you would use a feed-forward neural net because you're predicting Q values, and those Q values are going to determine what Mario does. If you're doing some kind of policy gradient, or like a PPO, or an A2C, or A3C, you're probably using you could use some kind of recurrent structure to keep track of your policy network. You could also use a feed-forward structure to do that too. So yeah, the answer, both. But man, if you want to talk about playing Mario using neural nets, hit me up later. I've seen all kinds of stuff on that front. That's one of the so I do a lot of games research, and that's a very, very common research topic in the area. So if you're using neural nets, of course, I should also say that you can accomplish that task using just good old-fashioned A-star search and do really, really well. Man, I really, really want to teach a game AI class. This is probably top of my list of classes that I want to try out. I think it'd be really useful, but anyway. I digress. So let's start with feed-forward neural networks. That's what we're going to start with. Because once you understand the structure of a feed-forward network and how you train it, a lot of those principles get used again for recurrent neural networks. Feed-forward neural network. So as I mentioned, you can think of it, well, briefly mentioned, you can think of it graphically as a directed acyclic graph that is a fully connected series of nodes. So it's a DAG, directed acyclic graph, with a fully interconnected series of nodes called neurons. Would they let you teach a game AI class? I've been lobbying for it for a while, but due to kind of just departmental constraints, there hasn't been room to let me do it. But it's still something that I'm going to keep pushing for. I thought I was going to get it a couple years ago because there was the big push to emphasize gaming in the curriculum. And I thought, hey, I can do this, and it'd be really, really cool, and I can guarantee you it'd be well attended. But then coronavirus happened, and so that's made things really, really difficult. But I'm still going to push for it. Anyway, yes. So a neural network. Yeah, you can think of it graphically as this interconnected set of nodes called neurons. Each neuron, and last time I mentioned that a neuron in this sense is essentially just like a computational unit. But the goal of that unit, so each neuron, is that it should fire or activate when a linear combination of inputs exceeds some threshold. What were the results of that push? Haven't noticed much gaming in the curriculum. It had to get put on hold. So they put out a big call within the departments, well, within the college, or the university, really, for proposals on ways to augment the curriculum. And those proposals were due, like, a week after the campus shut down the first time for coronavirus. And as far as I know, nothing, it was, like, we submitted a few proposals, myself and Dr. Ware, in conjunction with some other departments. But as far as we know, nothing was ever done with it. And so I imagine that due to like the budget cuts we've also had to go through, that a lot of the focus on that has been kind of put on the back burner. But that being said, we're still trying to get some stuff done to that front. It's just been a much slower process. I'm graduating, so I want to know when you teach that, if I could find it on Twitch. I mean, hey, I like this medium. Next semester, we're probably going to be back in the classroom, but I'll have to sit and think if I can come up with an easy way to kind of keep the videos going, because I do like having videos posted. I think it's useful. But we'll see if it's easy to get set up with, like, a classroom environment. Could it not be a 485G special topics? It definitely could be, but it's more complicated. It's not just like where do you teach it. It's given my other teaching responsibilities, how do you fit it in? Because special topics classes typically have a what's the word? Lower priority on having them taught a semester than other classes such as machine learning or AI. So, yeah. A lot of it is out of my hands. I do what I can by saying, hey, I want to teach this. I think it would be good. But, yeah, it is what it is. Yes. So, what a neuron's job is, what it's supposed to do, is it is supposed to, well, fire, activate, whatever that means, and we'll see what it means soon, whenever it sees certain inputs. So each neuron is going to take in information from every input. And in this case, your input, these are all inputs. These are your features. So if you have, if you were trying to train a neural net on the wine dataset, you would have 11 input values. Each of those is going to be connected to each of your neurons. And if ever a neuron sees a certain pattern, it'll fire. Yay, whatever that means. Fire. If it doesn't see that pattern, then it won't. It'll suppress that input. So the goal of a neuron is to either enhance or suppress information as it flows through the network. And this is kind of why the initial name neural network came up. This is why it was given that. It was this idea that, oh yeah, these neurons are all specialized, they're trained to do different things, and they fire when they recognize certain patterns. Are the neurons also referred to as the hidden layer, or is that something different? The hidden layer, which you don't always need a hidden layer, but the hidden layer is made up of neurons, yes. Yes, that is true. However, your outputs are also themselves neurons. But yeah, so that's the multi-layer neural network, which we're going to wait on just a second. For the time being, we're going to focus in on the single-layer neural network. The extension to a multi-layer case is surprisingly non-trivial. Anyway, we can represent a neuron as follows. So visually, this is what a neuron looks like. Is what a neuron looks like. So we'll just boo up, make it a circle. So are neuron outputs binary? They don't have to be. It all depends on your activation function, and that'll become very, very clear very, very soon. Actually, usually, yeah, they're not binary. They're usually continuous. Yeah, that's why I put activate and fire in quotes, because it doesn't actually, like, it's not a 0-1 kind of thing most of the time. So neurons, again, these computational units, have 3 parts. Well, first off, this first part is something we call in. It is the input. And remember, we mentioned that the input is just a linear combination of some input. X0, X1, all the way down to, we'll call this Xi. These inputs, they could be your input values that you get from your data set. They could be your set of input features. And for the time being, that's where we'll kind of stick. If you have a multi-layer network, they could be the outputs from one of the interior layers, but still you get your inputs from somewhere. And this first step in this computation is to calculate the linear combination of your inputs. Now, what this means is that you have some weights attached to all of these values, just like you did with linear regression. We're going to refer to these weights as W, though. Just because that's how, when I originally taught this, I did this. So 0J weights, 1J, and weights IJ. And so how you read this is the weight for the connection going from X0 to layer J. That's how we're going to read it for right now. And so this input is just the dot product of your inputs. This in value, is the dot product of X and W. So that's step 1. Linear combination of inputs. So once you have that, once you have your in value, you hit it with a nonlinear function, an activation function. And I'm going to just poorly draw that there. This is your activation function. This is what's going to determine whether this neuron, again, scare quotes, fires or not. And we'll talk about in a little bit the many different ways that you can define an activation function. But this is going to be, like, what determines the strength of your output. The result of this is going to be Xj. So the output of this gets sent off to other layers. So this would be WJK. And so this output could be used as the input at subsequent layers. Output weights. If this is the last layer of your neural network, then, like, there are no links leading out from there. This would just be your output. Do we train both the weights and the activation function? Nope. You select the activation function. You select it before you even get started. Before you even start training, based on the problem that you're faced with. And we'll talk about how you would select activation functions in a second. Well, hopefully, maybe we have time. So this is the task. This is what a neuron is. This is what it's doing. So, in other words, the output of a neuron and we'll just call that, because we'll stay with this example up here, we'll say xj, is just g, your activation function, times this weighted combination, or g of this weighted combination of inputs. Weighted combo. Inputs. This is essentially your linear regression formula. What's written above the sigma? Oh yeah, that's n sub j. Yep. And so this section, this like bit in here, should look very familiar, because this is what you're doing with your linear regression model, is you're calculating that weighted combination of inputs. Here, in a single neuron, you just have an extra step of, once you have that value, you want to send it through some other function, this activation function. So for a better example of how these get combined into a network, let's consider a single layer perceptron. This is where we're going to start. Also, I will use perceptron and feed-forward neural net interchangeably. And in general, these are used interchangeably. Feed-forward neural network. So, a single layer perceptron with one output, and in this case, 3 input features, would look like this. So first off, as in our regression model, you have a bias term, x0. You would also have x1, x2, and x3 for your input terms. You have one output, so I'll put little circles here. These are my input values. One output, y. Every, how to put this? Every node in the graph, every input is fully connected to every output. So in this case, boom, we end up with 4 weights. A weight between the bias term in the output, input 1 in the output, input 2 in the output, input 3 in the output. Now it's important to note that these, at the input layer, so you can think of this as the input layer, these are not neurons. These are just the input values from your example. So you deal with the raw X values at the input layer. The output layer, these are neurons. So don't feel like you need to run x0 through the activation function. Or x1 or x2. What's x0? Ah, I'm glad you asked. It's 1. I'm very glad you asked. I was just about to get to it. So yeah, as in the linear regression model, x0 is 1. Although I've also seen some people use -1. And either way works. It doesn't really matter. It functionally does the same thing. It's just that if you have... the only difference is between using 1 or -1 as your bias term is going to be the sign on W0. That's all. So in this example, in the single layer neural network with the single layer neural network with one output, you can calculate that as just G of W0, X0 plus w1 x1 plus w2 x2 plus w3 x3. And that's the model. That is the model that you try to learn. And so the goal is still to learn w values. And as we did with our linear regression model, you can also represent this using matrices. Oh, I've seen the bias as part of the neuron itself, rather than as an input to the neuron. Is this difference significant? No, not really. Not really. Because what would happen, well, you'll see what the, like, using the neuron as an input, like, what it'll look like, but you could easily make it just part of the neuron itself. It's going to do the same thing. So if you wanted to represent this using matrices, and I strongly encourage you to do so for this, probably even more strongly than I did for linear regression. So y equals g w transpose x, where w equals w0, w1, w2, w3, and x equals x0, x1, x2, and x3. And just to have this out here, this is a 4x1, 4x1. Perfect. So this is the feed-forward case with one output. But you could easily extend this to multiple outputs. So let's go back up here. Draw a little line. It's a single layer perceptron with 3 outputs. If you find yourself doing a multi-class classification, it might make sense to give yourself 3 outputs. If you're doing a classification where you're classifying based on a value that has, well, like 3 or more values, then it would make sense to, or it might make sense to do this. Everything now just, well, again, gets more connected because we have to draw weights between every input and every possible output. So this can be extended to a matrix multiplication for each layer, right? Yep. Yes, it can. But in this case, like, we're not adding layers just yet. But in adding outputs, it's still just a matrix multiplication. It's just one matrix multiplication. So we have our inputs. We have our outputs. Now we have y1, y2, y3. Same deal. Our input layer, these are not neurons, these are just values. But every input is still connected to every output. So every output node is going to be calculated using the weighted combination of your inputs. So this we'll call W01 because it's the weight that goes from x0 to y1. W02, W03. We'll come down here. This would be W31, and so on and so forth. So you can keep track of this in a matrix too. Oh, well, actually, hold on. I'm running out of time. No. So we'll just say that if you were to calculate this, like represent this as a function, it's the same deal. Y1 is going to equal G of W01X. plus W 1 x1 plus W2 x2 plus W3 x3. That's Y1. Yep. Y2 equals G W0 x0 plus W 2 x1 plus W2 x2 plus W3 x3. And so on and so forth. I don't want to throw the matrix representation of this at you at the end of class, so we'll start the next class with it. But you know that you can put this, like, store your weights in a two-dimensional matrix, and then thus you could get all of your outputs just doing a dot product between your inputs and your weights. In this formulation, when you have an extra neuron in each layer that always outputs 1 for the bias, feels like that might get complicated. You do have that. It can be a little tricky to keep track of, but there are ways that you can make it work, which I will go over. I have in my notes in another place how to deal with formulating it this way. So yeah, there are pros and cons. Like, in my view, by using it as... lost my train of thought. Oh, yes. By setting it up this way, you simplify it in terms of the number of... or, like, how you set up the calculations. Like, everything is going forward is a matrix multiplication. Everything going backwards ends up being a matrix multiplication. Whereas if you make it part of the neuron itself... it's just extra, like, again, you have to think about it differently, and yeah. But yeah, I don't think it's too complicated, but it is something that you do have to worry about. Okay, so next time I will show you hey, yeah, you can represent this as a matrix. But as we move forward, this is something I'm going to try to be better about, is showing you the matrix form of this, because that's all a neural network is. It's a series of matrix operations. One of the things that I stress here more than in any other section, do not make a node class. Do not make a neuron class. I guess, again, if you want to, you can. Yes! Oh, someone said it. Sorry, I just saw your thing. Will we be creating nodes like we did with the tree? So in my opinion, use matrices for the whole thing. Do not make a node class. Don't do it. Don't do it. Obviously you can if you want. I'm not going to stop you, but I think it complicates everything if you do that. No, I'm really glad that you asked that. I'm really glad. Do not make a node class. You can ask anybody from last semester. I did this pretty much, like, every week we were talking about neural nets. I would just remind people, please don't make a node class. So in my opinion, it slows down computation. It slows down training. It just makes it not efficient. And pretty much every implementation of a neural network that you'll see out in the wild is going to be based under the hood on just running matrix multiplications. And that's all it is. That is all it is. And the really cool thing about this is, yeah, training... or calculating your output, matrix multiplication, backpropagating your error, matrix multiplication. It's really convenient. Okay, so next time we'll continue with this. We'll probably get into training proper. So yay, more partial derivatives, because it turns out backpropagation is just a modification, slight modification, of gradient descent. This is why I order things the way I do. Okay, I'm very over time. Thank you for coming out. In terms of extending the network, wouldn't it be easier not to have to write out each multiplication? See, I don't think it's that hard. That's the thing. But this is something that we can discuss later. Extending it, yeah, right, as in adding layers. Like, I don't know. I don't think it's that difficult. It's just you add to a for loop. Like, each layer becomes one step in a for loop. And I don't think that's too difficult. But, again, it will come up as we go along. All right. So have a fantastic rest of your day, fantastic Thursday, and I will see you all on Friday. As always, if you have any questions, please send me an email, and I will catch you all next time. See ya. W0, W1, W2, W3, and Y. It's really just a value, but if you wanted to, you could just say, oh yeah, it's a 1x1, sure, whatever. Not necessarily helpful, but actually that will be somewhat helpful later. But for the time being. And so remember, your output you calculate very similarly to how you would calculate the output of a linear model, but there's this added wrinkle of the activation function. So in this case, y equals g, applied to the linear combination of your inputs and your weights. So in this case, that would be w transpose x, where g is your activation function, and we're going to talk about those shortly. So for a single output, things look like this. You can very easily extend this to multiple outputs. The main things that change are, well, now you have more weights. So if we have the same number of inputs, x0, x1, x2, and x3, but now we have three outputs. What's going to happen is, well, you have more weights, because every input has a weight between every output. Trying to be much more careful about drawing this, and then as I say that, I kind of mess it up a little bit. But there you go. Fully connected. So when we say that the network is fully connected, this is what we mean. There are every possible connection that can exist, and since this is a directed acyclic graph, this is every connection that could possibly exist between your inputs and your outputs. And I guess I should say that you can't connect inputs to inputs. This is every connection that you can make. W01, W02, W03, and on. And in this case, the notation that I'm using, the 0, 1, just indicates that this is the weight between input x0 and output y1. So this you could also represent as a matrix. It's just your x stays the same. Your x is still a 4x1. x0, x1, x2, and x3. Your W matrix, however, does get more complicated. And there are multiple ways, well, two ways that you could represent this, as with the, as in linear regression. You can store things row-wise or column-wise. So, for example, you could do something like this. W01, W11, W21, W31. W11, W12. Nope, that's... No, that's right. W11, How is it that I always mess this up? 02, W12, W22, W32, W03, W13, W23, and W33. And so this is a 3x4. This is a 4x1. There we go. And so in this case, this is just storing things row-wise. So every one of these corresponds to one example. So these are the weights. The first row are the weights associated with... hold on. With that are going into output 1. The second row, these are all of the weights that are going into output 2 from each of our input features. If I stored things this way, then my output is just G, still activating it, WX. No need to transpose 3x4, 4x1. My output, so like WX, is going to equal a 3x1, which specifically contains, well, kind of our Y values. It's going to be the dot product between the input and the weights. So we'll call this, oh boy, what? We'll just say a 3x1 containing dot product for each output. And I want to say in NumPy you can actually call an activation function, call a function on a matrix, and it will, or okay, you can set it up so that it will apply a function to each element of a matrix. I forget the name of the method that you use to do this, but I can find that when it comes time for this assignment. So any questions on this? Oh, another thing. You don't have to store things this way. You could go the other way, where every column contains the weights associated with a certain output. The only thing that changes there... Vectorize, is that it? Okay. Yeah, there's definitely, like, there's... I didn't think it was vectorize. But I still wouldn't be surprised if it was. Yeah, there's a way that you can apply a given function to just everything in a matrix, and that's really, really handy here when it comes time to activate your outputs. But yeah, so you could store this column-wise, so it would be a 4x3 matrix. Think that's right? Okay, cool. Then yeah, vectorize will be your friend for this assignment. So if you store things column-wise, you just have to transpose the weight matrix. So or y equals g w transpose x if w is column-wise. Okay. So the last thing that we're really lacking here in terms of, oh, what is my neuron? Like, what does a neuron do is, well, what is G? We've talked about pretty much every other element of the neural net, but we don't know what G is yet. So what is G? And the answer is it depends. There are a lot of functions that can act as really good activation functions. There is no one activation that is better or better than any other. Be the third endorsement for np.vectorize. Awesome. Then you know what? Vectorize is the winner. That's perfect. That is perfect. When it comes time for this assignment, it will be that will be, I think, one of the most important functions that you have. Other than dot product, but anyway. So, there are many different functions that you can use as reasonable activation functions, but they often have some qualities that are in common. So there's no one set activation function. But all reasonable ones will ideally have these two qualities. So the first one, the function should be active, in scare quotes, when it views the right inputs. So it should be active when right inputs are seen. In this case, active means positive. The addendum to this is it should be inactive when the wrong inputs are seen. So this is all the first criteria. When wrong inputs are seen. And here, inactive just means small, close to 0 or negative, something like that. Means small. Either negative or close to 0. It varies for the function that you end up using. So you want this to act as some sort of threshold. If you're above the threshold, you output a higher value. If you're below the threshold, you output a lower value. The second criteria is that it must be a nonlinear function. This is what gives neural nets a lot of their power, this nonlinear transformation you perform on your input. If you don't use a nonlinear function, and I should say, this isn't required, but it's recommended. Not always required. And I'll talk about some of the special cases where this, where you might not do this. But if you don't use a nonlinear function, you can show that the entire neural net, if you don't use a nonlinear function, at least somewhere in the neural net, you can show that the whole thing will reduce to just linear regression. And then all of this extra work you're doing on representation doesn't get you anything. Now, that being said, it is somewhat common to see linear activation functions used, so just no activation almost, used at certain points in a network. Like sometimes you use them at the output, but it's usually it's not the only activation that's used. Because if it was the only activation, you would just have a linear model, and then you're performing a complicated linear regression. Linear regression. And so you lose out on a lot of potential power. Okay, so given these two criteria, there are all kinds of functions that we can use as activation functions. Two of them were listed in the chat earlier. So the two that were mentioned were sigmoid and the rectifier function. At least I'm pretty sure it was sigmoid and the rectifier. Linear doesn't normally fit very well, right? No, it doesn't usually. It doesn't usually. However, there have been situations, so I do a lot of reinforcement learning, and there are situations where it is useful to have, at your output, the very last layer, to have it be a linear activation. There are some times when that's nice, but still, even then, earlier in the network, I'm using nonlinear activation functions. It usually doesn't fit well, but there are times when it could be nice to have it at the last layer. Usually you don't use them in the internal layers, though. So 3 common examples of activation functions. So the first one, and this is the one that we're using in this class because it is the easiest to work with and one of the most flexible ones, and that's the sigmoid function. Now, gaze and be amazed as I try to draw each of these. It's not great. So ni, g of ni. So the sigmoid function, you can think of it as... Okay, no... Come on. Okay, that's not terrible. You can think of it as a soft step function. You calculate sigmoid 1 plus e to the negative x. So in this case, so in this example, this is the g of n sub I is just 1 over 1 plus e to the negative n sub I. And so by default, sigmoid has a threshold at 0. If your x, or in this case your n sub I, is positive, then sigmoid trends towards 1. If it is negative, it trends towards 0. So it's a range from 0 to 1. Out of curiosity, so this is a soft threshold function, a soft step function. Is there any reason why the hard step function might not be ideal in this case? So the why might sigmoid be preferable to the step function? Where this is the step function. So 1, 0, n sub I, g of n sub I. Discontinuity? Yeah, that's pretty much it. More gradient information during backprop. That's another one. So I guess this is another thing that you typically want out of your activation function. You want them to be differentiable everywhere. Yes. It might be too rigid to try to fit the data. That is also true. So one thing we'll see when we go through the backprop, well, when we try to apply gradient descent to training these networks, you'll need to be able to calculate the derivative of your activation function. And so you want your activation function to be something that has a derivative everywhere. These rigid, like discontinuous functions, that's not always the case. In those situations, we might want something like sigmoid. There's also the benefit that this does have a fuzzy boundary, which is usually going to perform better in practice than a harder, like a more rigid threshold. Very good. Excellent. Now, one thing to note, well, actually no, I'll wait on that one. So that's sigmoid. This is going to be what we use in this class, at least on this assignment. The other common one that was mentioned was the rectifier, ReLU, which stands for Rectified Linear Unit. So classically, the rectifier is defined as simply max, 0, or n sub I. And so, boop. Again, g of n sub I. This would all be 0, 0, 0, 0, and then n sub I. So rectifier is notable because it is going to give you only positive values. If your input is negative, it's going to change it to a 0. Again, this has the problem of a very like rigid threshold. And so a common extension to this activation function is to give it a soft threshold, a soft boundary, which ln, the natural log of 1 plus e to the x, e to the n sub I. And that ends up looking, oh god, oh, drawing this. Yeah, we'll go with that, kind of like that. A soft threshold at 0. Actually, no, I know what I'll do. I'll give it a different color. Purple, yeah. There we go. And so that is ln 1 plus e to the n sub I. I want to say this is sometimes, I think this is, yeah, soft plus, sometimes called. Black. Now, question. Might there be situations where one is preferable over the other? Subsequently, why has ReLU become popular? So back when I was a grad student, this was before the deep learning revolution, or just at the beginning of it. Sigmoid was by far the most common activation you'd see. There are others around, but Sigmoid was the most common. Not by a whole lot, but it was still there. However, ever since convolutional neural nets came onto the scene, Rectifier has, I would say, taken that crown. And there is a reason for it, and it has to do with, well, the application. And so the question, why is that? Why would people choose to use Rectifier over something like Sigmoid? I think normally it works well for situations where data is like true or false, right? So Sigmoid works well for situations where data is true or false. And the reason that that's the case is because, well, its outputs are going to be between 0 and 1, which you can easily model false-true. Sigmoid works well in situations where your output fitting into that range is reasonable. So, for example, imagine if you had 3, and I ran into this frequently with previous versions of this assignment. So your assignment on this is going to be handwriting classification with the MNIST dataset. So what some people tried to do, you would have to classify, I think it's the numbers 1 through 5. So what some people tried to do is they said, okay, I'll make a network that has one output because I'm going to have that output predict if it's a 1, 2, 3, 4, or 5. It'll just give me the value for what the number is. But then they go and use Sigmoid as their activation function at the output. And that's setting themselves up for failure because Sigmoid can't produce values that are greater than 1. And so they would wonder, why does my code not work? And I would say, well, you picked the wrong activation. In that situation, something like Rectifier would work. So while I can't say that, one activation function is inherently better than the other, there are certain situations where certain ones are set up for success. So yeah, in the case where you just have a binary output, 0 or 1, Sigmoid is great, whereas Rectifier might not be so great because it could give you potentially unbounded positive values. The reason that Rectifier became popular is because deep learning was originally, its big application area was in computer vision. Computer vision. And so the input values that we were frequently looking at were pixel values. Pixels as input. And so pixel values exist typically on the range of 0 to 250, 255, 256. So it doesn't make sense to use sigmoid in that case, because you want values that could be, much larger than that. At the same time, there are other activation functions that can give you negative values. It doesn't make sense to use those because pixel values can't be negative. Enter the rectified linear unit, which can give you unbounded positive values, which ended up working incredibly well because it focuses on the positive side. So ReLU is the best fit for this. Now, this isn't the only reason that ReLU became like a popular activation function. It also has a very simple derivative, but that's one of the reasons that it works so well in practice. So the last activation... Actually, okay. Does anyone know of any other activation functions? There's one more that I'm looking for, which is my favorite. But I'm curious if anyone has heard of it, has seen it, has come across it in their travels. So this, I'd say, is probably the third most common, if you're not counting linear as an activation. So for this third activation, what's one of the problems with the sigmoid function? Hinge? Not quite... Not quite thinking of Hinge. So what's one of the problems... At least I don't think I'm thinking of Hinge. What's one of the issues with sigmoid? Logistic? Well, actually... No, it's not the logistic function. So one problem with sigmoid is that, again, it's bounded between 0 and 1. You still only get positive values. It's bounded on the top end by 1, asymptote at 0. Yeah, it's that asymptote at 0 that's the problem. Wouldn't it be nice if we could get positive and negative values? Is there a function that looks like this? Yeah, sigmoid is the logistic. Hey man, don't feel bad for not understanding anything. Stick around. I like having people here. Are activation functions ever switched out as hyperparameters? They're not, so I'll get to that. Is there a function that kind of looks like this? Because wouldn't this be nice to be able to say, I've got a threshold at 0, I can get positive values and negative values. Does this exist? The answer is yes, it does. It does. Cube-root? Oh, that's way too hard. This is the hyperbolic tangent function. Scale the sigmoid? I don't want to scale the sigmoid. Tan H. Hyperbolic tangent function. Which ends up being pretty much the same thing. The benefit here, the derivative of this, is just the sigmoid function. But anyway. So this is what I consider to be the third most popular, or third most common activation function. Now, typically where you see this, so it's, well, this is like sigmoid on a broader range. And you see this very frequently with recurrent neural networks. In recurrent neural nets, this is the gold standard. However, there are situations where you want to use this with feed-forward neural networks as well. In fact, I have a fun little demo that I want to show you that TensorFlow put out that uses tanh as the activation, and it's fitting. It's fitting because there we go. It's fitting because the class labels that they're trying to predict in this demo are 1 and -1. So it's like tailor-made for the hyperbolic tangent function. Oh no, oh no. Okay, there we go. Back. And so those are our activation, or those are some activation functions. There are plenty more. Really, the only limits as to what you can use for activation are, like, you really want it to be differentiable. But over time, these have kind of separated themselves as being very effective. What else? Yes, okay. One last thing I want to go over before moving on to kind of the next thing. So one thing that these all have in common is that there are threshold values involved. So one thing these all have in common is a threshold. One of the common questions that I'm getting with the regression assignment is, what role does the bias play? Or we kind of know what role the bias plays. It's your intercept. But here, the bias term functions somewhat similarly. The bias term, in this case, moves that threshold around. Bias term, or I should say the bias weight. The term is just 1, but the weight is what matters. W0 determines the threshold. Sorry, going back through notes. So one way of thinking of this, and let me just in my head make sure this makes sense. Yes. When j equals 1 to n w j I x j exceeds w0i, then a neuron is active. So this is just in general true. So the reason that you have a bias term, the reason that you really don't want to forget it, is that the bias allows you to shift these functions down the x-axis. And so that gives you more power for the things that you can, or more power to recognize different things. That being said, there are times where you can get away without a bias term, but the reason that you're able to do that would be because the threshold existing at 0 just happens to work for your data. So yeah, the bias term and the bias weight are very, very important in this scheme. So that's what they're doing. Okay, so those are all the parts of a neuron. And if there are any questions, please throw them into chat. Please do. So the next thing that I want to talk about is, what exactly does a neuron conceptually do? Like, what is its role in the neural network? We know what it does in practice. It is this, you calculate a bunch of things. But, like, what does it do for the neural net? What does a neuron do? So for me, for me, how I like to think of this is a neuron recognizes certain patterns. A neuron is almost like a miniature classifier that's meant to pick up on certain things. Recognizes small patterns in the data. And then, if you have larger networks, these can then be combined in order to recognize more complex patterns. So then the neural net combines these to recognize large patterns. And so when you're asking, like, oh, how many like nodes do I need, or in a hidden layer, this will make more sense later. But at some point, you'll get to design the architecture of your own neural net, and one of the things that you'll get to pick is how many nodes in my interior layers do I have. And there's no one answer, but oftentimes it comes down to, well, how many patterns do you want to recognize? The more nodes, the more potential patterns you could learn. But then you also run the risk of overfitting, because you're making your network more complex. So what do I mean by that? Hold on, I want to get this little thing, make sure it's maybe big. Okay. Yeah. So here we go. So this is something that was offered by TensorFlow, just a fun little example of what's going on in a neural network. So in this example, this is our data over here. Let me make sure you can see this. If anyone has trouble seeing this, let me know, and I'll try to make it bigger. Boop, maybe a little bigger. Yeah, this is good. Question, do the patterns that a single neuron can recognize always correspond with things that can be described intuitively, like edges? Not always, no. In visual data, yeah, but in the wine data set, it's not quite going to be something that intuitive. And in the example here, we're dealing with visual data, so we can look at a neuron and we can visualize it, and it's great. But in other data sets, that's not possible. But one thing that you can say is that it's always going to be based on some, it's going to be drawing its own little miniature decision boundary. It's just you can't always visualize that decision boundary. So here we go. So in this example, we have a very simple neural net. It is a multi-layer neural net in that there is this extra hidden layer. So you have your inputs here. In this case, our inputs are just raw x1, x2 values. It's coordinate data. We have 4 neurons in our hidden layer, and we can decide if we want more or less. And then we have 2 outputs. Or sorry, there are 2 hidden layers. So this is the second hidden layer, and our output is just one continuous value. We have one output node, and it's either 1 or -1 down here. The orange node or points are -1. The blue points are +1. And if we So this is a relatively easy data set to learn, but notice here the activation is the hyperbolic tangent function. Don't worry about this other stuff. Let's see what happens as we train. So very quickly, and I love this, we get caught at a little bit of a local optimum. So we very quickly are able to find the boundary here. When I ran this last time, it was able to break out of it. Let's see if it'll be able to do it. It's not gonna. Let's try it again. There it goes. So that time it very quickly broke out of it. And so as with... Can I pause? Yeah. So as with linear regression, training a neural net often relies on having a good, starting set of weights, and so you might try this multiple times. But so in the first case, we get caught at a local minimum. Second time, we break out of it. But what's notable, what I really want to focus in on here, are the values of these neurons, like what's going on inside of these neurons. So each of these is producing some output, and because this is visual data, we can represent this, we can draw this on a graph. And so it's drawing its own little decision boundary. So this first neuron recognizes the following pattern. It's finding and it's actually kind of wrong, it's trying to draw a single straight line that classifies the center bits, or I guess I should say actually the outer bits, the outer ring. And so it's able to I wish you could see me pointing at the screen here, and I can't, like if I take my mouse off of this, it goes away. Can you just stay there? Please stay there. No? But that's just one, that's what that neuron is trained to identify. And so if its input puts it in the orange section, it's going to output a highly negative value. The second neuron is trained to find a slightly different pattern, and so on and so forth. And now what's really cool about this is all of these get put together in different ways and go to the next layer, where these neurons are trained to identify slightly different things. The reason that these later neurons can identify this complex pattern is because they're operating on the outputs of higher level knowledge already. So these later neurons, their job is to put together the features that we identified earlier and combine them in the way that lets them classify more complex, or identify more complex patterns. And so the second layer, we get these fun little circle patterns that it identifies. And if you notice at this point, it's almost right. Here, funnily enough, it identifies the wrong pattern, but it realizes that this is the wrong pattern. And so if we look at the weight coming out of here, the weight is negative. So the neural network learns to take whatever comes out of this neuron and invert it, which I think is super cool. Whereas this neuron pretty much gets it right, and so its weight is going to be highly positive. So it's going to take whatever its output is and just let it on through. It's really, really cool. I also had fun with this. So here's just a testament to the power of neural networks. So here's a very, very complex piece of data, a fun little spiral pattern. We have to add in all of the features to really make this work. So with these additional features, and notice we've got something similar to the basis expansion process that we did in linear regression. So input 1 is x1, input 2 is x2, input 3 is x1 squared, input 4 is x2 squared, and then there are all these other transformations they do on your input. But in adding these things together, let's watch it train. So thinking, and it's got it. Oh, almost. Not quite. At this point, the boundary is, for the most part, right. And at this point, it's all right. So over time, and by altering these, just your weights, you're able to come up with some very, very complex decision boundaries. Okay, you're good. And this is one of the reasons that neural nets are so powerful. And so in here, each of them is learning to identify different parts, different pieces of the input data. These are then combined by later sections of the neural network, and then finally combined into one readable output. So that's what your neurons are doing. They are specialized pieces of computation. They're like specialized small learners that identify specific things or learn to identify smaller patterns in your overall data set. And so the more neurons you add, the more layers you add, the more complex patterns you can identify. But you still run the risk of overfitting as you do that. All right. Okay, so that's the little thing that I thought was really fun. I had a lot of fun with this when I first saw it, and so I thought, oh, this is kind of neat. And one of the questions that I very commonly get with neural nets is, what is my neuron doing? Like, what the hell even is this? And so here you go. Here's what it's doing. You won't always be able to visualize it in a very nice way, but it's always doing the same kind of thing. Okay. So, that's all for today. Next time, on Monday, we will start talking about how do you train this thing. I'd like to think that we have a general idea of what a neural net is, so the last thing that we really need to do is figure out how do we get those weights. We've seen how changes in weights can change the decisions we make, but now how do we get them? Spoiler alert, it's very, very similar to what we did with linear regression. There's a reason we do linear regression first. If you can understand that, you're most of the way to understanding backpropagation for neural nets. All right, well, thank you all for coming out. If you find yourself struggling, even the slightest bit with the assignment, please reach out, please send me an email. I don't want people to suffer in silence. I feel like sometimes, no matter how small the problem is, if you get, or how long you've been, kind of banging your head against a problem, reaching out, getting an external perspective can help. And I'd much like, it's much better for me if you reach out early, than go, down a wrong path for a long time. So please let me know if you're having problems. All right, well, true. Yeah, I've seen it happen so many times. And so I will mention it every time I can. All right. Well, have a good weekend. And yeah, I will see you on Monday. All right. Take care, everyone. See you next time. Call h of x, what that's saying is, what is the result, what is the output of your linear model? Yeah, that's all it is. So it'll be a scalar value. And so when you're calculating h of x minus y, that is also going to be a scalar value. So the whole array is supposed to give a single value. If by, again, reading into things, if by array you mean like your array of weights and your array of input features, right. In fact, no, don't minimize everything. Here we go. So if we're calculating h of x, and we assume that x is equal to this matrix of x, like input values, xn, we also assume the existence of a theta, which has associated theta values. I just keep wanting to write x. Theta 2, ... theta n. Then right, this is going to be, like the output, h, is going to be a scalar. So we can do theta transpose x, which is just going to be a scalar value. Because it's the dot product of those two vectors, of those two matrices. So yeah, you'll just get a single value out. And if you're doing stochastic gradient descent, if you're updating your weights after a single example, then yeah, you'll have, like, you'll just have a single value for a single example. If you're doing a mini batch update or a full batch update, you might have an array of these scalar values, because you'd have one for each data point, each example. But I suggest, if you're struggling to get started, focus on updating your weights after each example. Just do stochastic gradient descent. I think that's an easier way to break into things, even though it might not be, like, strictly the best way to do things for this assignment. I actually don't know if it's the best way to do things for this assignment, but I know that it is effective. So hopefully that clears things up. Please let me know if it doesn't, because I'm more than happy to, keep going into this until it's clear. Okay, good. Yeah, like in my code, what I do is I just, I take out one array of input values for a data point, then I make another, a list, then I make another list that has all of my theta values, and I just dot product them together, and that'll give me the output. Cool. It is important that you understand how this works, because what we're going to find is we're going to end up doing something incredibly similar to this for neural nets. In fact, this is a really good place to start. Well, maybe with just a little review. So remember, we've been talking about neural networks, which are these sometimes large interconnected networks of these units of computation called neurons. And specifically, we've been talking about feed-forward neural networks for the time being. Neural network. Go away, mouse. I want to be over here. Something that I've alluded to but haven't formally mentioned, and I might as well formally mention now. There are two types of feed-forward neural networks that we're going to talk about in this class. So the first type is a single-layer neural network, or a single-layer perceptron. And despite the name, in a single-layer network, you actually have two layers. Just go ahead and draw some connections here. And there. Cool. So in a single layer neural network, you have two layers. Misnomer. An input layer, which just contains the values corresponding to the features in a data point. So if I have, similar to this, my x value, one of these would correspond to x0. One would be x1, x2, x3, all the way down to xn. So however many features you have in in an example, you will have that many plus one features because of x0. So imagine that you're using a neural net to do the wine example for assignment 2. There are 11 features in that data set, or each data point has 11 features, so you would have 12 in this case because you have a bias term. Again, this isn't the only way you can think about the bias term, but this is the reason I teach it this way, because it's so similar to linear regression. Then you have your output layer. No matter what kind of neural network you're dealing with, you'll always have an input layer, you'll always have an output layer. This output layer, you have a little more control over. So your input layer is pretty much fixed. And that's because it is tied to your data representation, your features. The output layer you have some control over. It is more flexible. For example, imagine if you had a binary output. So example, binary output, or a binary class label. There are two different ways that you could represent this. You could represent this as a single output node. Output neuron. Or you could have two. So with a single output neuron, you would assume that the output of this neuron would either be 0 or 1, or somewhere on that range. But there's nothing to stop you from doing something like this. using 2 output neurons, where one, and it's almost like a one-hot vector. Actually, it is a one-hot vector at this point. So, assuming I had 2 outputs, what you would be saying is this should activate if output is 0, and this should activate if output is 1. And so at that point, your output layer starts to look more like a list of indicator values. And you can extend this to an arbitrary number of classes. So yeah, this is, again, you can decide for yourself how you want that output layer to look as long as it is sensible given your problem. Like if we were doing a multi-class classification and we had, I don't know, 10 values it could take on, you could represent that as 10 different neurons, like a one-hot. Or you could represent it as a single output neuron that could take on 10 values. There are situations where it will make sense to do it either way. It's up to you to decide when it's most applicable. Sounds like MNIST. It should sound like MNIST. Because that's what you'll be working on for the assignment. So it's like I'm setting you up to work with MNIST. MNIST is a handwriting data set that you'll become very, very familiar with. Yeah, let me think here. So I will say this. I'll give you some advice on how to choose which is which. Generally, numeric class values involve a single output, categorical class labels almost always require multiple outputs. Almost always require multiple outputs. So that's a rule of thumb. That is like a heuristic that you can use. This is not binding. This is not always the case, but usually it's a good place to start. Like I want to say for MNIST, if you're doing multi-class classification, you can treat it as a like even though those labels are categorical, you could accomplish it with a single data point or a single output neuron. I'm pretty sure. But most of the time, if you have numeric output, a single node will be enough, because you can just predict values along the range, along the numeric range of expected outputs. But if you have a categorical class label, you're going to want multiple outputs most of the time. So there you go, something to use when assignment 2 comes along. So the other type of neural network that we're going to deal with is called a multi-layer neural network. Makes sense. We have single layers. Why wouldn't we have multi-layer network? Or a multi-layer perceptron. Again, it's all the same, using it interchangeably. And the thing that changes here, this is where you get a lot of your customization. This is where you get a lot of your where you get a lot of control over how your architecture looks. So as with a single layer neural network, and every neural network that you'll ever make, you have an input layer and an output layer. But now what you do is you have layers in between these. I'm going to make this, try to simplify or make this a simple neural network, called hidden layers. And as with every neural network, all of the neurons in one layer are fully connected to all of the neurons in the next layer. So here, instead of, in a multi-layer neural network, instead of all of your inputs being connected to every output input is connected to every hidden node, hidden neuron, in a hidden layer. So let's just, there we go. Draw a little line here. Enter hidden layers. You get to decide what these look like. And when I say what these look like, I'm really referring to how many hidden layers do you have, and how many hidden nodes are in each layer. These look like. So specifically the number of hidden layers, number of layers, there we go. And then the number of nodes or neurons per layer. Now here I have less guidance that I can reasonably give about like how do you choose these things. I can give you some advice, but a lot of it is so problem specific that it's a trial and error game. Turns out coming up with reasonable architectures is more of an art than a science, which is the reason that in deep learning we use so many pre-trained networks. It can be so costly to actually do this training that once you find one that works for one problem, you're more likely to try to use it on a different but related problem. It's just how it goes. So, let's see here. Yeah, some advice on choosing hidden layers and hidden nodes. So the more hidden layers you add, the more power you have. A fun little finding is that if you have one hidden layer, you have the power to model any continuous function, any at all. Any continuous function. If you have two hidden layers, you can model any discontinuous function. And so really, after that, you shouldn't need any more layers. But in practice, that's not really true. Any discontinuous function. So this is more of just a fun theoretical thing that we have here. Technically, with two hidden layers, you can model anything that you would ever want to model. However, this says nothing to how many hidden nodes you need in those layers to make this make sense, to make this work. So as you add hidden layers, the likelihood that you overfit starts to increase. I want to say even now, the deepest layers don't go beyond 10 hidden layers. And even 10 is a whole lot. That feels like a whole lot to me. Maybe it's just the problems that I work on most of the time. 10 is where, you never go beyond that. But based on what I've read in Vision, in Control, in things like that, deep is no longer means really, really deep. For your number of hidden nodes per layer, it's the same story. The more hidden nodes you have, the more likely you are to overfit. But remember what a neuron is actually doing. It is identifying some informative features about your input, or combining previous features that you found, previous patterns, I should say, that you found, into new ones. And so the more hidden nodes you create, the more unique patterns you enable the network to find. So usually what happens is you start with a lot of hidden nodes early on, and you reduce them over time. So start with many hidden nodes, and then reduce over time. Reduce in subsequent layers. So like one thing that I see pretty frequently is people like to, start with 128, then go to 64, then go to 32, then go to the output. Again, these numbers are kind of picked out of nowhere, but it's more the pattern of reducing the number of hidden nodes that's important, I think. Would it ever be advantageous to manually set the weight between two nodes to 0 and fix that value, essentially disconnecting two neurons? So I will say that it is beneficial to sometimes turn neurons off. But usually you don't manually set that. Just because, like, you could, if you happen to know a lot about your network and, like, what exactly this connection was doing, but most of the time you don't know that. So this is one of the reasons that Rectifier is so popular, especially in vision. If you ever have a negative value, which wouldn't make sense for most vision problems, you just turn that neuron off. You set it to 0. And so that blacks out that part of the network for a little bit. Now, during training, it could be beneficial to do this, but you typically don't manually set that value to 0. So there's this thing called dropout, where you randomly zero out the connections or the outputs of different neurons, and it ends up make you train more effectively. We will talk about this, but dropout is, you can almost think of it like a regularization technique. It's meant to guard against overfitting by randomly getting rid of certain connections. So that way you're less likely to overfit. You don't use the full complexity of your model during training, so you're less likely to overfit. So yeah, there are times when it's useful, but you have to go about it a very specific way. Excellent question. That's very good. So yeah, that's a multi-layer network. You've got more power, but you also have more choice. We're going to start with single-layer networks, though, the easy case. I do want to say this before we move on. So, one of the goals that I always have with this class, every single time, is I want to, and this is not just for neural networks, but I feel like neural networks is the biggest culprit. I want to demystify machine learning. A lot of people that use machine learning are practitioners, and I use this term maybe a little derogatively, I don't know. They treat machine learning as a black box. It is this thing you throw input in and you get stuff out, and it's great. If we go about doing this, machine learning is this big mystical thing. It is almost like black magic. And I don't know, I see that as being detrimental to, well, whatever it is you're trying to do. And so one of the things I try to do with this class is demystify it. Open up the black box, show you what's going on under the hood. Because oftentimes what's going on under the hood isn't all that complicated. And I feel like if you know how that works, you're going to be more effective at using these tools. So for example, like, even knowing how activation functions work gives you a leg up on so many people and so many problems that you might run into. Why is my neural net not working? Oh, your activation function doesn't make sense. Why are you predicting 0 and 1 when you have outputs that can range from 0 to 5? You're setting yourself up for failure. Anyway, neural networks, you can think of them in a very similar way, or as very, very similar to a linear regression model. Oh, see, now I have to read the XKCD. I always... yes! The pour data in, stir it around, and get some output. That one, yep, that is... that's my job, essentially. But, anyway, so yeah, neural nets are essentially slightly fancier linear regressors. And so to point this out, let's see, neural nets are fancy linear regressors. So consider the following network, and I'm going to number these a little differently, but this is just to prove a point. 3, 4, 5. So here we have a multi-layer neural network. Assume that 1 and 2 represent your inputs. So we have x1 and x2. Because it's a neural network, everything is fully connected. So we have weight going from 1 to 3 here, so node 1 to node 3. We have a weight going from 1 to 4. Then we have a weight going from 2 to 3, and a weight going from 2 to 4. Then at our output layer, we have a weight going from 3 to 5, and a weight going from 4 to 5. What you can do is, well, you can kind of recursively define this network mathematically. So let's start at the end. How do we calculate our output? So x5, everything is just going to be x's from here. Again, just for this example. This is our output. Well, you calculate that, well, it's a neuron, so it is the activation function applied to the linear combination of its inputs. So it's g, whatever g happens to be, doesn't matter for this example. W3, 5 times x3, we'll say, plus W4, 5 times x4. Cool. Well, we can now apply this definition going back. So, like, W3, 5, W4, 5, we know what these are. These are weights that we're trying to learn. X3 and X4, however, not quite sure. But we can just, again, we know how to calculate them. So G of W3, W3, 5 times, so what is X3? Well, X3 is the activation of its linear combination of inputs. So X3, its inputs are X1 and X2. So W1, 3 times X1 plus W2, 3 times X2. Coming out plus... Oh, sorry, this isn't supposed to be there. Bad. Actually, let me make sure I'm getting this right. Nope, it is supposed to be there. Boop. It's like I'm programming in Lisp. So plus W4, 5, again, another weight, times G X1, 4, W1, 4 times X1, W1, 4 times X1, plus W2, 4 times X2. There we go. And at this point, we can actually define everything. Like, these weights, these are things that we learn, but every other value is either an input value, well, is an input value. Like, everything is just in terms of inputs. And weights. Like a linear regressor. In fact, remember way back when I said if you didn't have a nonlinear activation function, that that everything reduces back into linear regression? This is why. The only thing that separates a neural network from a linear regressor is this activation function. And kind of the, like, multi-layer structure, but we'll get there. Like, if ever you find yourself lost, if ever you find, like, and every neural network is like this, if ever you find yourself, feeling beyond your depth, just remember, your neural network It's just a slightly fancier linear regression system. In fact, how we train this is gradient descent with very, very minor extensions. So, this is your machine learning affirmation with Brent. With linear activations, the layers just collapse, don't they? Essentially, yeah. The layers end up being somewhat meaningless. Well, not meaningless, but yeah, it's, again, just going to be a giant linear function. And so you're back to regression. You still, I think, have... I think you still end up having this weird credit assignment problem when it comes to training it, but functionally speaking, yeah, it's a linear regression problem. Okay. Any questions? And I hope everyone is comfortable enough to just, like, if you have a question, go ahead and ask it, but I do want to pause every so often. Because we about to move into, boom, there we go, into training. This is kind of all of this is like introduction to neural net structure, and things like that. We only really have one thing left to do, which is figure out how to train these. And this leads to my pre-class question for today, which is, if we're going to use gradient descent to train these, which we are, do we get a free win and just apply the update equations that we've learned already? So assuming, and we are going to do this, so assuming a loss function, well, let's just say, no. Assuming a mean squared error loss function, can we reuse linear regression updates for a single layer perceptron? So in this case, and so remember, squared error, 1 over 2. This will be slightly different formulation. This is important to realize, but it's still, at the end of the day, going to be squared error. Locally, yes. You get the upstream gradients and use them to find the downstream gradients or something like that. So, I mean, you're right. The process we're going to go through is the same. But we can't quite just straight up reuse those update equations. It's the same, well, kind of the same loss function. Keep an eye on order. So this is expected output, or the true output. Ground truth, we'll call it. There's my prediction. This is the opposite order from how we did this in regression, and this does make a difference. It flips a sign later on. So yeah, we're going to follow the same process. However, there's one thing. Remember, what's the one thing, or one of the things that a neural net has that linear regression doesn't? Your nonlinear activation function. And so what that means is when we calculate when we're calculating the partial derivatives of our loss function, it means that this is going to get a little more complicated. It means we have to take that activation function into account. Chain rule, remember. So, the answer to the question is yes and no. Yes, we follow the same process. Nothing about that changes. We're still going to update each weight according to the partial derivative of the loss function with respect to each weight. No, because our how we calculate our output here in our loss function is slightly more complex, so we'd have to take it into account whenever we're figuring out these gradients. So yes and no. Yes and no. So yes, still using gradient descent. No, in that the equations are slightly different. Okay. So given this, what is the process? So the process. So step one. What was the first step in for linear regression? First, well, you assume you start with some random weights. So like start with random weights. And so yeah, so random weights. Typically, again, you're going to want to initialize your weights to have some positive, some negative values. I generally like to go uniformly sample from like a given range of positive and negative values. So like on the range of -1 to 1. For neural nets especially, you usually don't want to set things to all the same value. Because what that's going to do is that's going to make it so that your weights are correlated with one another. Like all the weights in a single layer are likely to be correlated in that sense. And not to get bogged down in this, if your weights are correlated, the likelihood that you overfit is higher. So, yeah, randomly set your weights. Okay. So, for each example, so this is more along the lines of stochastic gradient descent. So number 2, calculate examples in value. So remember, this is just the weighted combination of inputs. So if you remember back to when we were looking at the neuron, we called this value in. There we go. Next. So this is this is the pre-activation value of a neuron. So next, activate it. Apply the activation function. So here what we're going to use is sigmoid. So here sigmoid is, remember, g of n is going to equal 1 over 1 plus e to the minus n value. That's your sigmoid. Now, we'll make this 3a. Repeat until repeat for all neurons. Output neurons. So this is a single layer perceptron, which means all of our inputs are connected to all of our outputs. So what this means, step one, first step essentially, is calculate all of your output values. Y1, Y2. Now once you have that, step 4. Make sure I'm doing this 2, 3. Yeah, okay, this is right. Calculate your raw error. just like in regression. Raw error. In this case, remember, the order of things has changed. So y, yeah, we'll just do y minus g of n. So remember, your activation is your actual prediction value. So don't subtract the linear combination of inputs, subtract the activation, and that's how you get raw error. Step 5, perform a weight update. And this is what your update equation looks like now. So Wj equals Wj plus, still alpha, times error. All of this is still linear regression update. Times, here we go. Here's the change. G prime of n times xj. So this is almost exactly the linear regression weight update, except we add in the derivative of the activation function on x, or on your input. Or on n, we'll say. I don't want to confuse you there. For sigmoid, that is very simply sigmoid of x times 1 minus the sigmoid of x. Yeah, so you switched the order of g of n, but made it plus in the update instead of minus. Yep. Good eye. So, I want to make sure everybody sees what happens here. This is due to order of y and g in. So remember, back in linear regression, what was our raw error? Our raw error was prediction minus ground truth. And when we went to update the weights, we calculated it as theta minus alpha times all of this stuff. Here, the order switches. So even though when you calculate mean squared error, the signs don't matter, it does matter for the update. Which is why I do things this way, so you get to see it both ways. So here, our raw error is expected ground truth minus predicted. The order changes. In order to compensate for that, the sign changes on the update. So it's not weight minus alpha times all of this, it's weight plus alpha times all of this. So be very careful. Like, there's no... lost it. There's no reason you can't switch things around. You don't have to set like error up this way if you don't want to, but make sure that your sign is going the right direction. It will cause problems if you have it going the wrong way. So yeah, the weight update for a neural net, a single layer neural net, is simply that weight plus alpha times your raw error, now times this derivative of your activation function. This is why you want your activation function to be differentiable everywhere. And it helps that sigmoid has a very, very simple derivative. But all that times your original input value. Okay. Again, any questions, please stop me. I think I can go through a quick example here. For chain rule, does the minus in front of gn come into play? No, I don't think so. I don't think that will cause any problems. I think. Okay, so an example. And this will be the last thing we do today. So let's assume we have the following network. Very simple network. X1, X2, x3. I'm going to ignore the bias term for this example. We will add it back in later. Y. So we have W1y, W2y, W3y. So as with any kind of gradient descent, we start with some random values, but we also have our x1, x2, and x3, our feature values. So in this case, they're going to be 3, 2, and 4. Our random starting weights, W1y, W2y, W3y, are going to be 0.7, 1.5, and negative 0.2. We'll assume an alpha value of 0.5, and our ground truth y is going to be 0. So when we see the features 3, 2, 4, x1 equals 3, x2 equals 2, x3 equals 4, our expected value is 0. So let's go through and do a weight update here. So step 1, calculate in. So y equals, or let's do it this way, in equals 0.7 times 3. So 0.73. Wait, reverse that. 3, 0.7. Plus 1.5 times 2 minus 0.2 times 4. The linear combination of inputs. Will you show how to handle the weight updates for the bias terms in the next class? Yes, I will. That'll come later. I want to go through just one simple example of forwards and backwards. So this, in value, our initial unactivated output is 4.3. Remember, this is just the dot product between your inputs and your weights. 2. Calculate g of n. Well, we know what n is, so this is just going to be g of n equals 1 over 1 plus e to the negative 4.3. Cool. This is going to give us a very, very positive value. 0.987. Since we don't have a bias term, this is essentially saying our bias is 0. And thus we could easily infer that because this was a positive in value, that we were going to end up with an activation near 1. 3. Calculate the raw error. I hope you can hear Carl. 0 minus 0.987. So remember, this is expected, this is ground truth, minus predicted. Truth minus predicted. Because this was our predicted value. And then finally, we 4, do the weight update. And I'll show it in this case for W1y. Although at this point, you could do all of the weight updates. So W1y is going to be equal to W1y, 0.7, plus 0.5 alpha, times the error. This is error, negative, this is negative 0.987. 0.987 times, and this is the derivative of your activation. It's easy to get lost here because they look very, very similar. So this is going to be 0.987 times 1 minus 0.987. So after if you calculate all of this out, if you want to do the math on your own time, because I'm running out of time, you'll end up with 0.681. So a slight drop in weights. And just to label all of these things, this is W1Y, this is alpha, this is error, and this is G prime of N. Okay. I'll go back through this example next time. I kind of went through very, very quickly. But then, if you were doing this for real, you would repeat this weight update for each of your weights. So you do this for W1 or 2Y and W3Y as well. So next time, I'll run back through it. We'll add the bias term back in, and I will show you how you can use or set this up as a series of matrix operations. It's going to be very similar to the linear regression case, but again, the bias does complicate things a little bit. Okay, so that's all for today. Whew. We are getting through. We are getting through. Hopefully this is all very approachable. This is all not too confusing. If you are finding yourself a little lost, please let me know. I'd be happy again to answer any and all questions that you've got on this. All right. Well, thank you all for coming out. Have a fantastic rest of your Monday. Remember, I do have office hours later today, so if you have questions about the assignment, I will be there to answer all of them. Or if you have questions about anything. I like answering questions. All right, well, have a fantastic rest of your Monday and a very, very good Tuesday as well, and I will see you next time on Wednesday. Take care, everyone. Bye-bye.